in this session, we will have two amazingly talented people who will in the talk, Augustin Vanrietvelde, about causality, and I was told just now about Augustin, it's going to be a fight session. So I think, I've had many lives, and one time actually was a bouncer for a while, so I'll deal with it. Okay. Augustin.
Alright, it's a pleasure to be here. It's going to be preparing for the fight in the next session. So we're just heating you up.
Oh, we are really warm.
Not enough. Alright, just to say very general stuff about this talk before it starts. It's going to be very conceptual, very high level. I try not to talk too much about my research, more try to set a very general conceptual stage here. So a lot of what I'm going to say is going to be vague. I apologize for this. And also, as I said, I'm going to mostly present things to talk about and real issues and conflicts in the community. And I'm not going to talk so much about how to solve them. That's your job. And I don't think that can be done by a single person or in a single year. Also, I'm going to talk more about space-time than about quantum gravity, because I realize I don't know enough about quantum gravity not to say anything stupid about it. So I will let the QG people say whether what I'm saying about space-time also applies to quantum gravity. I'd be interested in their opinion on this. Okay, so let me first set the stage what I'm going to say. So it's been 6 years of this. It's been amazing. I loved it. I was at this first conference in Hong Kong in January 2020. Great time. We went to the beach. Chastav told Carlos something on the beach about reality not existing. It was really amazing. And this 6 years of this have been really amazing. I've met a ton of great people. I have a friend who told me once that the real quantum gravity is a friend who made moved away. This is really true for me. On the scientific level now, I think what we got from this is also that we are doing some very hard stuff. I think we are still 6 years later in a situation where quantum gravity and quantum information still a good portion of the time took past each other. We have difficulty understanding each other. So to talk about these two communities, let me paint in a few very broad strokes what is quantum information, what is the structure of space-time, and why this quantum information structure of space-time initiative sometimes turns into quantum information versus the structure of space-time. So on the one hand, you have quantum information. Let me describe it in kind of very broad terms, in kind of the attitude it denotes. In quantum information, this is characterized by the fact that we will usually encounter these concepts: qubits, Alice and Bob, a lot of talk about agents, a lot of talk about abstract measurement outcomes and their correlations. But for instance, you don't care how you got these correlations. If you care about bell inequalities, you don't care whether you got them out of polarization or spin or whatever else, or even gravitational limit of freedom. This is irrelevant to the discussion. It's the typical attitude of quantum information. Also, quantum information loves its star models. Everyone uses star models, but I think the quantum informational ones are particularly brazen in their attitude. So in general, I would say the attitude of quantum information, is to abstract away the physical specifics. You want to care about as little physics as necessary. Typically in bell inequality violations, you don't care about which degrees of freedom are involved. I would say generally this is an aesthetic attitude. This is the attitude of someone who wants to know as little as possible about the world. They want to look at the world through a pinhole and get one qubit through that pinhole and just say something about that qubit. The structure of space-time side of things is quite different. In the structure of space-time side of things, you will see stuff like metrics and manifolds, like the Lagrangian of the universe, lots of infinities all the way, field theories. I also include QFT in that. I think QFT belongs more usually to the right-hand side. I'd say the attitude, and once again, this is very broad strokes, right? But the general attitude of people in that community would be more to talk about everything, have a full picture of the world, right? Like talk about the whole of space-time, or at least, okay, hello, Mr. That's great for the, for what colleagues. Okay, not necessarily. I would say, at least if I wanted to really stress the contrast with quantum information, I would say that there is kind of an exhaustive attitude more prevalent in people who care about the structure of space-time. Okay, and my point is these two communities, these two attitudes still clash at several points. Okay, from there I will make two claims. My first claim is we have to accept the clash. The clash is there, and we are not going to wish it away. We have to work through it. We have to work through the dialectics of what this clash can bring about. And maybe by having this, civilized fight, we can bring progress. The second claim, this is Angel here. The second claim is that the notion of causal structure is a particularly interesting, critical clashing point. And that by focusing on this notion and arguing thoroughly about it, maybe either we can bring progress. Okay, so to talk about causal structure, let me first say what both communities mean by causal structure. And here again, this will be very broad. In quantum information, we have to distinguish between two notions of causal structure, first order and higher order. So I'm going to follow the quantum causal models of Barrett and Orishkov here about quantum information. First order causal structure is about the causal structure between points in the past and points in the future. So I'm using a space-time description here, which I shouldn't because I'm talking about quantum information, but just to give you intuition, an illustration. You're talking about the causal structure from all of these points in the past to all of these points in the future. And the point is, for instance, P3 might be might have no causal relation with A1, for instance, because it's too far away or for whatever reason. So to model this, you will model it with unitary channels. Unitarity is very important for several reasons that I won't go into too much detail about. And for instance, let me describe the simplest case. You're going to say, okay, I have a unitary channel with two inputs and two outputs. And I want to say that one of the inputs has no causal influence over one of the outputs. You can actually define this in lots of ways. All of these ways turn out to be equivalent. Let me describe one. You take the unitary channel and you discard the other output C. Then this is the same thing as if you had discarded the input A. This is meaning that because A doesn't go to D, if you discard C, then A has nowhere to go. So that gives you a very solid definition of causal influence in quantum information. But that's only the first order definition. A very important point is that, to be general, we have to put a higher order. What do I mean by this? I mean, what about situations where you have three events and you might have A before B before C? So for instance, you're doing, once again, a space-time illustration, you might have situations where A is there, B is there, but then you have more convoluted relationships between them than just one past layer and one future layer. What people in quantum information have proposed is that this cannot be modeled with the previous method. We have to go higher order with supermaps, unitary supermaps. What's the point of a supermap? And by the way, for the people who know process matrices, this is the same thing as the process matrix. Process matrix is the Georgia-Minkowski version of the supermap. The supermap is something, let me take the comparison with channels. Unitary channels take states, they map them to states. Supermaps take channels and map them to channels. So a supermap is an object like this that takes in, say, n channels and maps them to a big channel made out of these n channels. And so you can really think of it diagrammatically as inserting stuff into slots. Each of these slots corresponds to a channel that has a certain input and a certain output. A typical supermap would be to say, okay, I have two channels, A and B, and I turn them into A then B, into the composition of B after A. Or another supermap would be turning them into the composition of A after B. And here you see, for instance, how the supermap obviously will describe the causal structure, the causal order in that case. Another very well-known supermap is the quantum switch that Victoria already talked about this morning, where you can create a controlled superposition of the two causal orders. Okay, and from that you can get a well-defined notion of causal influence by using the previous definition in the first order, because from the supermap you can get literally, you can study the causal structure of that solution. So I'm not going to go into the details there, but I really want to insist on the fact that higher order is paramount to the discussion. Then how do you study causal structure in space-time? That I can go fast about. I mean, everyone knows about this. This is the relationship between points in the manifold. This is determined by the metric. The metric will determine whether any two points are space-like separated, or time-like separated, or light-like separated. In particular, this causal structure, as long as the metric is fixed, as long as we are not solving everything together, but for instance in fixed metric, it is agnostic to the specific dynamics that are taking place. It is constrained on the dynamics that are taking place, that they have to satisfy this causal structure. Okay, now let me talk a bit about why it is important to inquire about causal structure in both theories. On the quantum information side, there is of course a very natural argument, which is that Bell equality violation in quantum theory is the failure from your classical notion of causality. So in that sense, it is obvious that quantum theory has something very interesting going on with causality. There's also another more refined argument that I like a lot, which comes from Rob Steckens. It comes from this very interesting programmatic paper he wrote 13 years ago, where he makes this point that in a theory you have kinematics, you have states, you have dynamics, evolutions of those states. And he makes the point that you can actually change the kinematics if you kind of contrariantly change the dynamics in such a way that the theory stays the same, gives the exact same prediction. And so in that sense, these are not really, these cannot describe independent reality. And so he goes on to argue that only a kind of union of the two will preserve an independent reality. You need to find a kind of gauge invariant, using the word gauge invariant here in a very loose way. The gauge invariant aspect might be causal structure. This might be the union that preserves an independent reality. I think this is a very interesting argument as to why causal structure might be important to quantum information, quantum foundation. Let me move on to why causal structure can be considered to be very important on the space-time side. This argument I'm stealing from the proponents of causal set theory. It's the Hawking-Alleman theorem, which I think does not necessarily lead you to causal sets, but I think it's very important. The Hawking-Alleman theorem, which also bears the name of other people related to me these two for readability, tells you the following thing. You can take a space-time and say, I want to have a certain causal structure on it. So you fix the relationships, time-like, space-like, light-like, between any two points of the manifold in the consistent form. Then you want to say, well, what are the metrics that are consistent with this causal structure? It turns out that not many are. In fact, this uniquely fixes the geometry of the manifold up to conformal transformations. That is, up to your volume factor. So, in a very good sense, it means that the metric of your space, the geometry of your space-time, is nothing but its causal structure and a volume factor. And you can argue that the causals, because you have, I think, 10 gauge independent parameters per space-time point, you can say that, in fact, 9/10 of your metric is a causal structure. So, to a good extent, the metric is almost just the causal structure, and studying the causal structure is studying the geometry, if we forget about the volume. So, this is, of course, here again, a very broad argument, but I think this might make us believe that causal structure can be considered to be fundamental in space-time physics. Okay, now on to the interesting part, the disputes. I will present 4 disputes between the two notions and 1 consensus. The consensus will surprise you. Okay, let me start with an extremely naive and vague definition of causal relations, just to give some illustration. This will have the philosophers in the screen. But I think everyone would agree there must be some kind of truth to that statement. To me, let's A and B are causally related if modifying the situation at A affects the situation at B. Okay, I will identify 4 points of clash in there. The first starts with always the first word, event. Causal structure is a relationship between events, but what is an event? The second one is that this is about modifying situations. To talk about causal structure, you have to talk about intervening. And what is an intervention? How should we deal with it, conceptually speaking? The third point is that I'm talking about affecting, but shouldn't it be may affect? Shouldn't it be saying that if I modify the situation at A, this might change the situation at B, or is it that it does always change the situation at B? And finally, what do we mean by affecting the situation? Surely by this we should mean something that happens to the operational outcomes, and how do we treat this? Okay, but before I talk about this, these four disputes, I'm going to go on to talk about one point of consensus between these two theories, and that point of consensus is time symmetry. I cannot stress this enough. Both notions are covariant under inverting the arrow of time. In particular, the spatiotemporal one obviously is. The quantum informational notion I just presented is covariant under inverting the arrow of time. Therefore, we can all be happy with this. I do think that as a community in 6 years of QISS, we have spent a lot of time talking about the arrow of time, and this was an interesting discussion. I do think there are way more fierce and interesting fights to have about causality than that about the arrow of time. And Bob actually promised me that during the discussion session he will balance out any question about the arrow of time, and I'm counting on him. Okay, let's go on to the interesting dispute. The first one is what the hell is an event? There is no notion of causal structure without a notion of an event. So what do the two theories have to say about it? On the space-time side, where you see the kind of diagrams, it's quite obvious that an event should be, maybe at first approximation, a point on your manifold. Of course, then you have to be a bit careful about this. The point of the manifold doesn't mean anything by itself. You have to look at, you have to take into account the whole arguments that Victoria already presented this morning. So maybe you should take the equivalence class of those points, the diffeomorphisms, and covariantly change the content of the universe and say that this might be more of a good point. Another possibility, which goes back to Einstein, is to consider it even more physically, I guess more operationally, as an intersection of world lines. When two things collide, then that should definitely define a point, that is an event. Okay, what about quantum information? Well, in quantum information, you see diagrams like this, where you just have Alice, and Alice gets a system, maybe measures it, maybe does something on it, outputs the system, Bob does the same. This is from the Oshkosh-Bruckner paper. So here the notion of an event is more relaxed and possibly more interesting, but also quite more vague. The possibility is to say, well, this is why an agent acts, but what the hell is an agent? Well, an outcome is obtained, but we are going to see in a while that it's unclear also what you mean by the place where an outcome is obtained. Let me show that in a more concrete case, because this point of debate has actually been well identified by the community on a concrete case, the switch controversy. So fortunately, Victoria told you a bit about it already. So I told you about this quantum switch, which is this supermap in which quantum control qubit decides whether you have event A before event B or event B before event A. You can create superposition of these two possibilities. Well, people in Vienna have claimed to have implemented the quantum switch through this optical apparatus. And of course, we are all theoreticians, so we don't want to look too much at this. But the point is that depending on its polarization, either the photon goes to A, goes back, and then goes to B, or it goes to B, goes back, and then goes to B. And if you look at if you do tomography on the system at the end of the day, you realize that the mathematics of the quantum switch describes the situation. But people give very different accounts of this. The first account, the spatiotemporal science, is very like exemplified in this paper by Pankovic and Bojinovic, where they say, oh, well, let's show this is happening in Minkowski spacetime. No one denies this. So let's look at what happens in Minkowski spacetime. At time t1, either you apply A or you apply B. At time t2, there is another event, A prime. which is the potential application of the gate A at 22 minutes, other events be fine. So we have 4 events, and there is no switch happening. The 4 events are in a well-defined causal order between them. And that all obviously comes from the fact that we define events as pointing in Minkowski spacetime. As soon as you put this definition of events, the result is absolutely obvious. Pointing in Minkowski spacetime will never be in an indefinite causal order. So the answer is really your assumptions about playing the event. There might be criticisms to this though. In particular, you might say that A and A prime, they are alternatives. They are different branches. They never happen jointly. They happen in superposition, and whether superpositions happen jointly is of course a difficult point. But there is an argument to be made that you cannot consider this as two separate. Okay, on the other extreme, you have the quantum informational side, which is well exemplified by Augustin Vanrietvele's notion of time-delocalized subsystems, where he says, I can identify events in the switch, and we need to go fast about this, but as factors, you take the tensor product of the systems at different times, and we factorize it, and within this you find the hidden subsystem, which is what the agents are. That's how we do that. Okay, I think on this we have made some good progress towards the synthesis. In particular, so you saw already this paper that Victoria presented, where they precisely show that these two descriptions are actually related by a quantum control diffeomorphism. To me, if I wanted to talk about a possible resolution, I would say that symmetries play a central role in that discussion. But I'm not going to talk more about it because actually Vilasini, so as far as I understand, will revolve precisely around this question. And she seems to have very interesting results to present, so I'm definitely looking forward. Okay, the second dispute I think is not as well identified, but it is as important, and of course related. It is about intervention. Let me first make an obvious statement. You cannot talk about causal structure if you don't have a notion of intervention, that is a notion of changing stuff. If nothing ever changes, you cannot talk about something influencing another thing. You just live in a ridiculously boring block universe. So what is a good intervention? First, here I want to be humble about what I say about space-time physics. I might be lacking some of the details, and I would be very interested in people predicting me. But it seems to me that usually people in space-time like to change their boundary conditions. They like to take a Cauchy surface and they say, okay, let me plug a different state inside the Cauchy surface. I apologize about the ugliness of the diagram there. And then I take a Cauchy surface in the future and I look whether stuff has changed on the Cauchy surface in the future. My point is, this is only about changing the kinematics. You're only changing the states on the Cauchy surface. You're plugging a different state, if you want, in your dynamics. On this, I am not completely certain. It might in particular be different in algebraic QFT. I'm not sufficient expert. What I know about is that at least in quantum information you have something very interesting, and that's where I go back to this notion that causal structure in quantum information is a higher order thing. It's described by a supermap. And your interventions are changing the unit trees you plug in the supermap. You're changing the local dynamics. And I think this is a very odd thing once you start thinking about it. If you want to describe the universe, the dynamics of the universe is fixed. This is given by the Lagrangian of the universe, the eternal laws of physics. How come you could suddenly decide not which state you plug in, but which evolutions you perform? To me, this is really an open question. But I think if you take seriously this notion, this is literally what it's saying. And I think this has not been realized enough. This is related to the process ontology. You can refer to the thesis of Nick Ormond if you are interested. So in this picture, where people only pick the dynamics of A, B, C, and D, you have 300 of the dynamics, and my point is it is revolutionary. Maybe in a bad way. Maybe it is meaningless. I'm saying this seriously. I have no idea. I think we ought to debate this. And yet, I think we haven't so far. And I would definitely see this as an interesting thing to discuss in the coming years. Okay, I have two other disputes, but they are much more, much simpler, maybe less important. The first one is about whether causal structure is a constraint or a property. In space-time, unless you consider gravitational back action onto the gravitational field, you say you start with a metric, and then the causal structure is just a constraint on which dynamics you might put in that metric. And the constraint of what may affect what. In the quantum informational notion I introduced, you start with the dynamics. By the dynamics, I mean the global dynamics now, the supermap. And this is your dynamics. This is what's going on. And then your causal structure is not any kind of constraint, it's a property that captures what are the causal influences in this specific dynamics. So this is also a point that I think is an interesting difference. I think, just to say something quite vague about this is about the conceptual priority of space-time over the specific dynamics. Is space-time constraining the dynamics, or is space-time just an aspect of the dynamics? Finally, there's the role of measurements, which of course will come into any kind of discussion of quantum theory. In particular, if I go back to this question about events, now I went fast about this. I was talking about plugging unitaries into the supermap, but you can also plug, measurements, VODNs, if you want, in the supermap, and then you say, well, I get outcomes. Now, agents dealing at those events get outcomes in these events. And it's come around in particular in discussion of the switch that it's very unclear how you could get events in the switch, and when people say how you could get outcomes during the switch, when people say, oh, I can perform the optical switch and get an outcome in it, other people show a Minkowski space-time diagram and say, no, you got the outcome later, when you recreate the information you captured at the two different events that correspond to what you call the event. This is essentially about moving the Heisenberg curve. You can always move, as we all know, you can always shift the Heisenberg curve when you do a measurement. And therefore, saying that you take an outcome at a certain event will always be liable to a counter-argument that, no, you obtain it later, because people will move the Heisenberg curve and say, oh, the big agreement or whatever happened later in my perspective. That's the first thing. The second thing, which here again, I apologize for the bad quality of the diagram, is to say that, as far as I understand, a lot of the time in space-time physics, you look at situations like this. You consider kind of the boundary condition in particular, you consider that at the boundary you need classical people, and you measure kind of transition amplitudes to a small quantum region. So you just have this tiny quantum dot inside the classical world. The view that comes from supermaps is very different. You have just small classical agents living in the quantum soup. They get the classical outcomes locally, but the whole universe around them is quantum. Okay, that ends my discussion of the disputes. For good measure now, I will talk a bit about my work, but I think it's relevant because this is also about a program trying to bridge an equivalence between operational and relativistic global structures. Is it the end already? Okay, very, very quickly. My point is that you have two notions of causal structure in two possible notions in quantum information. One is the causal structure that I presented to you. The other is compositional structure, saying that an unitary U decomposes like this. This is a much more mathematical, structural kind of notion in its small space-time. The interesting point is that these are actually equivalent, and more generally, you can devise a research program of trying to prove the equivalence in general. These are equivalents in the very simple situation I described, but in general, the equivalence is still to be proven. And this is a very interesting equivalence in my opinion, because this is about the equivalence between what I can prove at a phenomenological level and what might be going on deep down in the universe. And our results recently that proved this for 1D quantum scalar automata, which are a discretized model of 1D spacetime. I'll go very quickly, so with my collaborators, we showed that they are always causally decomposable. So you can see this as an equivalence between a quantum information like notion of causal structure, causal operational, and the existence of fine-grained dynamics. And this works at any causal way, which is okay, so just some lessons. First one is we should fight, very formally. The second is that causal structure is a nice thing to fight about. the notion of events, a nice thing to fight about. I would be interested in the possibility for the freedom of the dynamics in the supermat formalism for its revolutionary potential, and finally, like photo decompositions might prefer mathematical tools. It's not about the concepts, but it's about mathematical theorems that might help us reach the end. Okay, thank you very much, and I'm looking forward to